Alrighty, welcome back to another video. So today we are looking at linear independence with a set of vectors. And before I go into what exactly, or I guess how to go through with this example problem, I think it's important to define what linear independence is, first of all. So when we say a set of vectors is linearly independent, so we'll say, suppose we have a set of vectors v1, v2, all the way off to vn. This set of vectors is linearly independent if and only if, I think that's an if and only if statement, correct me if I'm wrong, x sub 1 times v sub 1 plus x sub 2 times v sub 3 all the way down to x sub n v sub n is equal to 0. So if this statement here is trivially true, only trivially true. So what this is essentially saying is that provided this set of vectors v1 through vn, if we take a linear combination of all of those vectors with weights x1 through xn, then we set that linear combination equal to 0, and if this equation is true only trivially, which means that x sub 1 is equal to x sub 2 is equal to dot 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 x sub n, and all of these values are equal to 0. So if x sub 1 through x sub n are 0, and that's the only way to make this equation true, then this set of vectors is linearly independent. So applying that to this problem here, we're going to do the same exact thing. So we're going to say, we'll say let a generic solution vector be equal to x sub 1, x sub 2, and x sub 3. Then we'll say is x sub 1 v sub 1 plus x sub 2 v sub 2 plus x sub 3 v sub 3 equal to 0, only trivially true. So that's what we're trying to figure out. That's our goal here. So what we're going to do is we're going to expand this guy out. So we have x sub 1 times v sub 1, which is 1, 2, 3, plus x sub 2 times v sub 2, which is 4, 5, 6. And finally, v sub 3, 7, 8, 9 is equal to 0. And then we'll factor these guys in. And if you haven't noticed already, this is forming a linear system. Let's do the last distribution. I keep saying factoring things in, I mean distribute, sorry about that. It's equal to 0. We'll turn this into an augmented matrix. I'm just going to skip the linear system part. I hope you can see what's going on here. So I meant for that to be the 0 vector, not just 0. So we should have 1, 4, 7, 0, 2, 5, 8, 0, 3, 6, 9, 0, and that is our augmented matrix. So now we're going to go through some row operations. So we'll say r sub 2 goes to r sub 2 minus 2r sub 1 you know, what I'll probably do is come right back, because this is going to be pretty tedious. Alright, so after some row operations, we stopped, or I stopped at row echelon form. And the reason I didn't continue on is because if we look here, we have a pivot column, we have another pivot column, then we have a non-pivot column. So they're basically, when doing row operations to prove that a set of vectors is linearly independent, you want to watch out for two things. One, you have a non-pivot column or more, or two, you have an inconsistent linear system. So if you have either of those issues, then your set of vectors is linearly dependent instead of independent. So we'll say because we have a non-pivot column, v1, keep writing my one strange, v2, v3 is linearly dependent. So if you want a conceptual kind of understanding, I mean, we defined v1, v2, and v3 to be vectors in R3. So what this is saying is that one of these vectors, whether that be v1, v2, v3, we could write one of these vectors as a linear combination of the other two. So there's there's a dependence there, which becomes pretty problematic when we try to do like actual linear transformations and stuff like that. But anyways, that's pretty much it. Thank you for watching.